So, hello everyone. Today's lecture is about the electric motor actuators, and the most important electromechanical actuator in automobile is an electric motor. Electric motors have long been used in automobiles from the beginning of the starter motor, which uses electrical power supplied by a storage battery to rotate the engine at sufficient RPM that the engine can be made to start running. Motors have also been employed to raise or lower windows, positioning the seats, as well as for actuators on airflow control at the idle position. In recent times, electric motors have been used to provide the vehicle primary motive power in hybrid or electric vehicles. There are a great number of electric motor types that are classified by the types of excitation that can be DC or AC, the physical structure, and example for that is the smooth air gap or the cell-in pole type, and the type of magnetic structure for rotating element rotor, which can be either a permanent magnet or an electromagnet. Regardless of this motor configuration, each motor is capable of producing mechanical power due to the torque applied to the rotor. By the interaction of magnetic fields between the rotor and the stationary structure, that is stator. Now we will discuss about brushless DC motor. A brushless DC motor is not a DC motor at all, in that the excitation from the stator is AC. However, it derives its name from the physical and performance similarity to the shunt connected DC motor with a constant field current. This type of motor incorporates a permanent magnet in the rotor and electromagnetic poles in the stator as shown in this figure. Traditionally, permanent magnet rotor motors were generally only useful in relative low power application. With the recent development of some relatively powerful rare earth magnets and the development of high power switching solid state devices have substantially raised the power capabilities of such motors. The stator poles are excited such that they have magnetic north and south poles with polarity with currents IA and IB. These currents are alternatively switched on and off from a DC source at a frequency that matches the speed of rotation. The switching is done electronically with a system that includes an angular position sensor attached to the rotor. This switching is done so that the magnetic field produced by the stator electromagnet always applies a torque on the rotor in the direction of its rotation. So the torque equation is given here. The torque applied to the rotor by the magnetic field intensity vector H created by the stator winding is given by a vector product, where M vector is the magnetization vector for permanent magnet and gamma is the constant for its configuration. The direction of this torque is such as to cause the permanent magnet to rotate toward parallel alignment with the driving field. The magnitude of the torque is given by the letters Tm and is equals to the product of gamma, M magnetization vector, H magnetic field intensity, and sine theta, where theta is the angle between M and H. If the permanent magnet rotor were allowed to rotate in a static magnetic field, it would only turn until theta is equals to 0. In a brushless DC motor, however, the excitation fields are alternatively switched electronically such that a torque is continuously applied to the rotor magnet. In order for this motor to continue to have a non-zero torque applied, the stator winding must be continuously switched synchronous with rotor rotation. Although only two sets of stator windings are shown in this figure, normally there would be multiple sets of winding, each driven separately and synchronously with rotor rotation. So for the simplicity of the understanding, only two set of stator windings are taken here. In fact, the sequential application of stator currents creates a rotating magnetic field which rotates at rotor frequency. A sensor S measures the angular position theta of the rotor relative to the axis of the magnetic poles of the stator. A controller determines the time for switching, current IA and IB on, as well as the duration. The switching times are determined such that a torque is applied to the rotor in the direction of rotation. At the appropriate time, transistor A is switched on and electric power from the onboard DC source, example the battery pack, is supplied to the poles A of the motor. And brushless DC motor diagram, control diagram is given here. The duration of this current is regulated by controller C to produce the desired power. After rotating approximately 90 degrees, current IB is switched on by activating transistor B via signal sent by the controller. The rotor permanent magnet is equivalent to an electromagnet with DC excitation. Omega R is equals to 0. The frequency at which the currents to the stator coils are switched is always synchronous with the speed of rotation. Thus, the frequency condition for the motor is satisfied since omega S is equals to omega M. This speed is determined by the mechanical load occurring on the motor and the power commanded by the controller. As the power command is increased, the controller responds by increasing the duration of the current pulse supplied to each stator coil. The power delivered by the motor is proportional to the fraction of each cycle that the current is on. Now, in the upcoming lecture, we will discuss another electromechanical actuator, that is the stepper motor. Thank you for your time. Have a nice day.